Alrighty, so continuing our little conversation about piecewise functions, sort of the second piece of piecewise functions, I want to talk a little bit more about graphing piecewise functions. That'll actually be the last thing that I do in this video, but I want to talk about this aspect of it, which we haven't even looked at before, either in a video or in class, which is writing piecewise functions from the graph. So starting with a graph, can you write f of x equals and then what that looks like? Okay, we'll end with some additional practice graphing. I'll do one more problem just to sort of show you how they look on delta math, because I know some of you struggle with using delta math. Unfortunately, it's what we got right now, so we got to make it work. I got to be a little flexible and try some stuff and you know, persevere through struggle. It's not that bad to not know how to do something right away, as long as we figure it out, right? But this is sort of where I want to start, writing piecewise functions from graphs. So let's take a look at a graph of a piecewise function. Here we have it. I didn't make this up. I just sort of Googled piecewise function and grabbed the first thing that I saw. And the goal here is I want to be able to write f of x equals, and then those big curly brackets, and then two equations. It looks like it's going to be two pieces, right? For two different chunks of the domain of this function, it looks like I have two different rules. One of them I'm going to highlight in red would be this line right here. Okay, so I'll sort of do that one first, just because, you know, reading from left to right, that's the first one. And the other one, which I'll highlight in, let's do orange, would be this line right here, right? So this line right here. Ugh, terrible. Okay, but you get the idea. I just want to make sure it looks a little bit neater than that. It's sort of hard to be neat on a writing tablet. There we go. Okay, so I'm going to do a red equation for the red line and an orange equation for the orange line. Now, writing equations of these lines is easy enough. Normally the lines have arrows on them, right? But I can see pretty clearly just from looking at this line, the slope of this line is 1, right? Up 1 over 1, up 1 over 1, so m is 1. And then all I really need is a point. Well, I mean, I have this one, I can see the y-intercept is 1, right? So that's easy enough to write. It's y equals mx plus b, y equals 1x plus 1. So x plus 1 is the equation for the red line. If you like point slope, I mean, there's a point at 1, 2, so you could do, you know, x minus 1 plus 2, which works out to be x plus 1 anyway, okay? So that's sort of the equation of the red line. Now, the other thing you have to think about is, what is the domain? What's the sort of piece that you put over here, right? So sort of next to the x plus 1, what do I write? And it looks like this is sort of the rule for my function from this point here, where x is equal to -4, to this point here, where x is equal to +1. So it looks like from between -4 and +1, that's what my piecewise function is going to look like. The red part that is y equals x plus 1. Notice I use less than or equal to for both of them. That's because these are closed circles. They're like solid dots, not open circles. So I know that at +1 and at -4, this is the equation I'm going to use. If I plug a -4 into this function, I should get a -3 out, because that's where that point is. And lo and behold, I do. And if I plug a 1 into this function, I should get a 2 out. And lo and behold, I do. 1 plus 1 is 2. So I've handled sort of the one half. Now I have to look at the other half, right? So the orange piece that I've highlighted in orange. Well, again, I can sort of tell the slope, and I can sort of see where the y-intercept is going to be, or use a point or something of that nature, right? But clearly here I have, like, look, I have a slope of -1. And if I were to write this equation, let's say point slope form, I have a point right here, which is 3, -3. So I would do, okay, y plus 3 equals -1 times x minus 3. And that's fine, that's point slope form. The only thing is, if I'm going to use function notation, I have to make it look like y equals. So I'll do y equals -x minus 3 minus 3. Okay. Of course, it does simplify to just be y equals -x. If I do a little bit more math, distribute the -3 minus 3 is 0. I just get -x. But it'd actually be cool if you just left me that. That's fine. You just have to make sure it's y equals so that you can write it in function notation. But in any case, that would be the equation of the line if it was sort of a full continuous line going from -infinity to infinity. But in this case, I don't want the whole thing. I only want this little chunk from x equals 1. From x equals 1 to x equals 3. So I need 1 is less than x is less than or equal to 3. And again, hopefully you see pretty quickly why I did less than for the left bound and less than or equal to for the right bound. 3 is part of this line, right? When x is equal to 3, I do have a point there, but 1 is not. 1 is an open circle. And in fact, if I put less than or equal to here, right? If this were less than or equal to, and this were less than or equal to, then suddenly I would violate the main thing that makes a function, which is that every x value has exactly one y value. I would end up with 2 y values for that x value of x equals 1. Okay, so there you go. I've written my piecewise function for this particular piecewise graph, right? Let's look at another one, and this one's a little bit more complicated, a little bit more pieces of my piecewise function. But again, I'll try to highlight them all in a different color. I may run out of colors though. So here here's sort of the first piece of the piecewise function that I'm drawing in red. Then in orange, we have this horizontal line right here, which is just going to be a y equals -2. I can do that one almost immediately. And then I'll skip yellow, and green's not really going to show up on this background, so I'll do light blue for this part. Okay, so then that'll be my third piece, and then my fourth piece. I don't know what happened there. My fourth piece is going to be this piece right here. Okay. And there's not arrows on here because I just sort of copied it off of Desmos, but they're sort of implied that this keeps going forever, right? Kind of backwards and forwards. So if I were to write my piecewise function, it's going to have 4 different chunks to it, right? So my f of x is going to have 4 lines this time instead of just 3. So I'm going to have to write a little bit more conserving of space. As far as the red line goes, let's see, the slope of this looks like it's -1/3. It's kind of hard to see because I drew all over it in red, but let's erase my red for 1 second just so we can confirm that that's the slope, right? Looks like every time I go up 1, I go back 3, right? Up 1, back 3. Is each one of these spaces 1? No, they're not. Yeah, that's a little complicated, isn't it? Okay, so this is up 1, this is back 2, 4, 6. Okay, yeah, so 3. So it's -1/3 any way you slice it, right? It's either up a half and back 3 halves, or you got to look at the scale, right? But certainly the slope here is -1/3. Okay, so then I have y minus y1. Let's use this point right here since this point is pretty convenient to use. Looks like that's at -3, 4. So y minus 4 is equal to -1/3 times x plus 3. And of course I would have to add 4 to both sides to get this as y equals, and then it would look like -1/3 times x plus 3 plus 4. And you can write that as y equals mx plus b if you want. I don't really care. That's good enough for me. The only thing I got to think about now is the domain. So where is this the actual rule for my function, and where is it not the rule for my function? So kind of looking at this, it looks like there's a closed circle there, and that closed circle is at x equals 3. It's halfway between -2 and -4, so it's x equals -3. So this is good for all values that are less than or equal to -3. Anything bigger than -3, I will not be on this line, but we've handled the red one. Okay, so notice how I start by writing the equation of the line, which we've practiced a million times. It was on your last quiz. Everyone should be pretty comfortable with that, and then I consider the domain afterwards, okay? The orange line has a slope of 0. It's horizontal, so that's just going to be y equals -2. The x value can be whatever you want. The y value is always -2. So -2 is going to be my next block. Looks like I only want that to be my rule between the x values of -3 and 0, right? So it looks like between -3 and 0, that's going to be my rule. Of course, I use less than signs because there's open circles on either end of that chunk, that piece of my piecewise function, so I certainly don't want to use less than or equal to there. There's a bit of a gap here, but that's okay. We don't really need to think about the gap just yet, but there's actually nothing that goes on between 0 and 1. And then we look at the part that I previously had highlighted in light blue. Looks like a slope of 2 here, right? Up 2 over 1, up 2 over 1. Okay, so that's going to be a slope of 2. And then if I need a point, well, let's see. Here's a point up here. We'll use that point twice because that point's 3, 5. So I'll do y minus 5 equals slope of 2 times x minus 3. So if I add 5 to both sides, I get 2 times x minus 3 plus 5 is what y would be equal to. Okay. And again, for the domain on that one, looks like my lowest value is 1. My biggest value is 3. I'll include 3 in the domain here. I won't include 1 because there's an open circle there. Which leaves me with just one more piece to go. And again, I have to erase what I drew because I can't really see it. The slope is -1 pretty clearly. It's down 1 over 1, down 1 over 1, right? So I have -1. And again, I have that 0.35, which is actually on both the purple line and the blue line. So I can use it again and write y minus 5. This barely shows up. Is equal to -1 times x minus 3. I don't really like how that color is showing up. Do I have another light color? Would yellow show up better? Yeah, yellow's way better. -1 times x minus 3. Okay, so I'm writing it in yellow even though over here it's purple there. Now you can see. So I have y equals -x times x minus 3, or -1 times x minus 3 plus 5. And of course that would simplify pretty nicely into -x plus 8, right? But I can do that kind of in my head. Or I'll just leave it because who cares? It's correct. Correct is correct. -1 times x minus 3 plus 5. And that's what I want my graph to look like when x is greater than 3. Now, technically, I could do greater than 3, or you could say, well, it looks like it's a closed circle, so can't I do greater than or equal to 3? It doesn't really matter, because if you plug a 3 into either this equation or this equation, you'll get the same answer of 5. We sort of constructed it that way, so it doesn't technically matter. Even though it's a closed circle, you might say, yeah, greater than or equal to 3 makes more sense to me. If you do greater than 3, though, it's just you get the point from the blue one, and then you don't get it from the yellow one. Okay, but either way, it's good for me. Typically, we don't want to do greater than or equal to 3 and less than or equal to 3, because then it looks like there's 2 different rules you can use for f of x at that particular x value, which is kind of sketchy, right? So I just made one of them less than or equal to 3 and one of them greater than 3. It doesn't really matter which one you choose. But there you have it, okay? If you can write the equation of a line, it's just really that with a little bit of extra work to sort of determine the domain for each individual chunk. Check for open circles versus closed circles to determine if it's going to be greater than or equal to, less than or equal to, and that's all there is to that, okay? So that's writing piecewise functions from graphs. Let's talk a little bit more about graphing piecewise functions, just because, again, I want to show you on Delta Math how this works. So if you kind of feel good about Delta Math, you maybe just want to stop the video here. That's no problem. It's going to run a little longer than my videos normally do, for sure. But we're going to look at this as three different pieces of my piecewise functions. I'm going to show you sort of how to sketch a graph on here, and then once we have our graph, we can compare it to what we see in Delta Math, and I'll show you sort of how that works. So I have 1/2 x plus 4. I can draw that without worrying about the domain right now. If I start at 1, 2, 3, 4, there's a point right there. Right? It's really hard to draw points on this because it always thinks I'm doing something I'm not. And then the slope is 1/2, so I go up 1 over 2, up 1 over 2, like that, or down 1, back 2, down 1, back 2. I want to get to -4 because I know that that's sort of a relevant point for me, right? So I should certainly try to get to -4, but it's really hard when it won't let me draw circles. There we go. There we go. And there we go. Okay, so that's sort of my my line right now. But remember, I don't really want all of these points. I only want from -4 and less, right? So less than or equal to -4 is really all I want. So I don't really need this guy or this guy or this guy or this guy, but the rest of them are good, right? So those 3 points sort of define my line for me. I can sort of draw that in just like that. Okay, so there's sort of the first piece. So this is done. Then I have y is just equal to 2, positive 2. Between -4 and +1. So I'll do that in green just so that you can see that I'm now in the second chunk. Y equals 2 is just a horizontal line, right? So it's just sort of stretching all the way across like this and back, okay? But I don't want that whole horizontal line, so I shouldn't have put the arrows on there. I actually only want it between the x values of -4, which would be right here. Hey, look at that. It's a closed circle on top of an open circle, so we just draw it as a closed circle and the closed circle fills in the space. And then this goes all the way to x equals +1, which is right here, and then that would be the open circle. Okay, so this is taken care of. The vertical or the horizontal lines are always the easiest. And then we have 2x plus 2 for x greater than 1. And I'll do this in red. I'll draw the line first. So 2x plus 2 would actually start right there, right? And then a slope of 2 would put me up here, up here, up here. Stop doing that. Up there. There we go. Okay. And again, I don't really want the point where x is equal to 0 because I only really care about this graph from 1 onwards, right? So sort of from here onwards is where I want it. And there we go. Okay. So it looks like we have sort of a good picture of what our graph should look like. This is done. It sort of starts at the point -4, 2. And goes backwards with a slope of +1/2. Then it's horizontal until we get to the point 1, 2. And then there's an open circle. It jumps up to the point 1, 4, right? And then it has a slope of 2 and continues onward from there. So graphing this is not so bad. Putting the graph on Delta Math could be a bit of a challenge, though. So let me pause real quick and pull this one up on Delta Math, and I'll sort of show you how you sketch this exact same graph that I have here on Delta Math. Okay, I have my screen adequately split so that you can kind of see this was what I came up with. Here's Delta Math. You can see it's the exact same thing, right? So I just need to sort of transfer my work to Delta Math, which is sometimes easier said than done. I'm going to start sort of with this point right here, which is at -4, 2. So I'm going to put my cursor at -4, 2. I'm going to click, and then I drag, and it'll automatically start drawing a line. I can put the line anywhere I want, but I know my slope has to be a +1/2. So I'll sort of drag it to that point, and then I can keep going to that point, and so on. And you'll see that it'll just draw you a line segment. Now I don't want a line segment. I want an array, right? Basically, right? Well, if you click on the endpoints, it converts them. So if you sort of go through the options, it'll either give you the arrow at the end, it'll give you a closed circle or an open circle. So I've successfully drawn this blue piece right here, right? Now the green piece, I'm going to start here, and I'm going to, again, stretch. So I clicked on that point, and now I'm dragging my cursor. I can drag it wherever I want, but I want it to be a horizontal line that stops when x is equal to 1. Now again, I want an open circle there, so I convert it to an open circle. And then finally, my last piece, I know it's going to start at over 1 up 4. So over 1 up 4 will be right here. And again, I have to click and drag, and the slope is 2. So I'll just sort of draw a little chunk that has the proper slope, a slope of 2. Notice how I went like up 1 over 2, or up 2 over 1, up 2 over 1 like that. And again, I need it to be an arrow because this sort of continues for x is greater than 1. Okay, and that's how you draw the graph in Delta Math. You have to click and drag to make a line appear, and then you can click the endpoint to change it to whatever you want. And hopefully it's right. If it's wrong, it's going to be really embarrassing. Oh, thank goodness. Okay, yeah, see, it's exactly the same way that he drew it. Okay, unfortunately, they don't really give you much feedback for what you did wrong on these. But yeah, if you sort of have your original graph and you can kind of make the conversion, it goes much smoother than just trying to do it straight from Delta Math. Of course, you can probably try to do it straight from Delta Math. It's not necessarily impossible, but I would certainly recommend you do sort of a sketch first in your notes. Okay, cool. That's all I have to say about piecewise functions today. I will see you guys next time in class. Thank you very much.